Okay. So we're going back to the constant acceleration equations. And in 1D, the variables that we have are the time, t, the acceleration, a, the initial position, and this is the position at the instant when time is equal to 0. Then we have p, that's the position at time t. Then we have v0, that's the velocity at time equals 0. And then we have v, and that's the velocity at time t. Okay, and then is that all of them? Yeah. So we have 6 variables, and we have 3 equations. The first one says v is equal to v0 plus at. The second one says p is equal to p0 plus v0t plus 1/2 at squared. And the third one says 2a times the quantity p minus p0 is equal to v squared minus v0 squared. Yes. I did say I forgot to do a cheat sheet, but this is sort of like a cheat sheet. Yeah. Wow. Great minds think alike, even when they're both me. And then in free fall, the acceleration is 9.81 meters per second squared down. And when an object is its highest point in a projectile motion, yes. Okay, so that's 1D, and you're pretty used to that stuff by now. So now 2D. I want to just emphasize what's the same and what changes. So a lot of these things aren't just numbers anymore, they're vectors. We still have the time t. That still has the same meaning. But now the acceleration is a vector. And it has components, ax and ay. And that's the acceleration vector. One question about this, and it also relates to the acceleration in 1D. So I break up position into the position at time 0 and the position at time t, and then velocity into velocity at time 0 and velocity at time t. Why don't I do that with the acceleration? I only give one acceleration. Why is that? It's because these equations are specifically only applicable for a constant acceleration. And so in general, yes, there is, like in general two-dimensional problems, general one-dimensional problems, acceleration changes over time. But for these equations, whatever the acceleration is at one instant is the same at another. Okay, so that's why, I have to break this. I don't have to break up the acceleration into time equals 0 and time final. It's the same. Then P0x and P0y are the components of the position vector when time is equal to 0. Then Px and Py are the position vector at time t.
Is that the initial position vector for the original one?
Yeah, P0x and P0y. Yep. And the meaning of initial position is at time equals 0. Yep. Position vector at time t. Then we have V0x and V0y. And that's the velocity vector at time equals 0. And then the last one is Vx and Vy. Bless you. And that's the velocity vector at time t. Okay, so if we go back to 1D, the number of variables we have available for our equations, 1, 2, 3, 4, 5, 6. Okay. And our 3 constant acceleration equations, those are the only variables that we have to deal with, so that's the only thing that appears in those. And there are 3 equations. So now if we go down to 2D, how many variables do we have? Well, it's still basically the same idea. We still just have time, acceleration, initial position, initial velocity. But now each, except for time, which is not a vector, each of the other ones is split up into 2 different components. And so now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 total variables that can come up in the equations. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. And the equations, I'm still going to write them as equations 1, 2, and 3, but I'm going to split each one of those up into an x component and a y component. So 1a is going to be the x component equation that says px, in the same order I did in 1D. So equation 1a says bx is equal to v0x plus ax times t. And equation 1b says vy is equal to v0y plus ay times t. And then 2 equations make up what was equation 2 in one dimension. So 2a says px is equal to p0x plus v0x times time plus 1/2 ax t squared. And 2b says py is equal to p0y plus v0y times t plus 1/2 ay t squared. And then equation 3a says 2 times ax times the quantity px minus p0x is equal to v squared minus v0x squared. And the last one, 3b, it's all the same stuff, but with y components. So 2ay times the quantity py minus p0y is equal to, this should have an x on it. Okay, so is equal to vy squared minus v0y squared. And so even though we still have like the same 3 forms of equations, now we have 6 total equations. Okay, so even though the ideas are all kind of the same, the bookkeeping issue becomes bigger, you know. I want you to notice a couple of things about these. What equation, what variables occur in both x and y equations? Okay, this is going to be an important thing, an important fact to use in these problems. Well, so we're going to think of the separate components as separate variables. Okay, so yeah, like p occurs in x and y equations, but the variables are px and py. And if you look through all of them, you never see a px in a y equation. Okay, and you never see a vy in an x equation. There's only one variable that you see in both of them: time. Yeah. And so that's going to be a really useful thing. There are going to be a lot of cases where we're trying to figure out something in a y equation. And I guess it'll more often go the other way. So let's say we're trying to figure out what the final x position of something is. Okay. But first, we're going to use the y equation to find the value of t, or something like that. Okay. It's the one thing that we can use the other equation and then plug that value into, use it, the y equation to find t, plug it in, and use it for x. So only time. Everything else is vectors. And that means that, for the vectors, for the vector components, the x components always stay in the x equations. And the y components always stay in the y equations. So when I was talking about one dimension, I went through the variables, went through the equations, and then I talked about two things that we use all the time in free fall problems. So one was the fact that the acceleration is 9.81 down. And the second one is that at the highest point in an object's flight, the velocity is 0. And in two dimensions, there are versions of that too. So in free fall, first, the acceleration vector now is equal to 9.81 meters per second squared down. You know, that's a vector now, and if we choose our positive y axis to be up, which is what we're usually going to do, then this vector is, the components are going to be 0, negative 9.81. Excuse me. And then second, at the highest point in an object's flight, you might think that the velocity vector at the highest point is going to be equal to 0, but it's not exactly that. The vertical component of velocity is 0. So if we have the y-axis pointing up like we usually are going to, that means that the y component of velocity is equal to 0. The x component of velocity doesn't have to be 0. Now I want to give you sort of something to think about to, make it clear to yourself that that's true. So imagine a guy standing all the way in the outfield of I was going to say Metrodome, but that's gone. But anyways, whatever it's called, Target, whatever. Yeah. Okay, so this guy stands way back there, chucks this ball as hard as he can, this pro baseball player, like all the way to home plate. Somewhere in its flight, it reaches its highest point. Okay. And imagine that you know exactly where that highest point is going to be. Okay. So here's this guy. I was going to say Torrey Hunter, but he's in an old folks home probably now. I guess I don't follow baseball much anymore. Okay, so this baseball player just chucks this ball. Here's the ball. And you've identified where the highest point is going to be. So you set up a ladder. And you stand up there. And you just wait. This is you. Okay. And you're happy enough about it because you expect the velocity to be 0 when the ball gets there, which means right as it reaches the highest point, it's going to just gently nuzzle up against your forehead. And you can just like pick it, and look at it. Because if the velocity is 0, it's at rest, it's just sitting there. Okay, don't do this. So at the highest point, the y component of velocity is going to be 0. It's not going to have any motion up or down, but it's still going to have a very, very large x component of velocity. And it's the x component of velocity that would hurt there. Okay. So the idea here is the velocity vector is not 0. Um, Anybody have any questions about any of this? Yes. Yes. Yes, that's exactly right. Yeah. Um, so yeah, if you throw a ball straight up into the air, you could still treat it as a two-dimensional problem. And if your y-axis is up, you'd have interesting stuff happening in your y equations, and you'd have nothing happening in your x equations because everything would just be zero. Yep.
If you throw in a forward, then the velocity gets zero, right?
The
Like if you throw the ball straight at the x component, it will be the velocity will be zero, right? Or
the x component of the velocity would be something, and the y component of the velocity would be zero at the start. But then acceleration would make the path start to curve, and so then it would have both. Okay, so who remembers what the first common misconception was? You should remember this because this will be on quizzes. Yeah, that's right. So it was that gravity makes heavier objects fall faster. It turns out that gravity doesn't make heavier objects fall faster. Air resistance just has different effects on their motion, and that's why in a lot of cases a heavier thing ends up falling faster. Okay, so here's common misconception number 2. Um, in free fall problems, the motion along one axis, one coordinate system axis, affects motion along the other axis. That's not true. So actually, what we saw looking at those equations is that no x components cross over to y equations and vice versa. And so what happens along one axis is happening totally independent of what's happening in the other axis. They have no effect on each other. And this is, okay, no effect on each other. And here's the example I want you to associate with that. So let's say there's one person here. Um, and this person reaches out and, okay, this looks like a big bullet because it's a small picture, but the idea is this person just drops a bullet straight down to the ground. Okay, why does it have to be a bullet? Well, that's because of this other guy. So standing with his back to this guy is another guy holding a gun. Well, this guy has a little more of a weight problem and a head shape problem. It's Gru from. Okay, and this guy fires a bullet horizontally. So here the bullet is dropped. And here a bullet is fired horizontally. And these bullets are both going to hit the ground. And the question is, compared to each other, when are they going to hit the ground? Yeah, and so they are going to hit the ground at the exact same time. If you have enough space for the bullet to hit the ground before it hits the wall, you know. Most people's intuition tells them that something about the really fast horizontal motion of the bullet that's shot is going to keep it from hitting the ground as fast as the one that's just dropped straight down. I think that intuition comes from the fact that the bullet's going to leave your vision so fast that by the time maybe you'll never even see it, but by the time you would lose sight of it, it wouldn't have really dropped at all. And if you shot it in a room, it would hit the wall at basically the same height that you let it go from, because it hits the wall so fast, you know. But think about what the initial velocities are of these two bullets, okay? So if you just drop this bullet straight down, you're releasing it from, it has the initial velocity of whatever it's dropped from, which is the ground. And so it has 0 velocity at the time that it's dropped, okay? And the one that's shot, say it's going 1,000 meters per second, okay? That might be too high, but it's a nice round number. So it's shot perfectly horizontally. So what are its velocity components? Well, it has an x component of 1,000, okay? But its y component is 0 because it's being shot horizontally. And so what equation are you going to use to see when it hits the ground? You're going to use y equations only, right? This one has a 0 initial y velocity and 0 initial x, but 0 initial y. This one, even though it's going fast horizontally, has a 0 y initial velocity. And so the y equations that govern these are going to look exactly the same, okay? The y equations don't know that this is going screaming fast horizontally. Okay. So I want to show this Mythbusters video where they do it because it's kind of cool. And then we'll go through and do some calculations related to that.
What you got there?
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus, they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, Jude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the...
Okay, so yeah, what? That's 0.0, just under 0.04 seconds. There are a couple of reasons that could happen. That they were off a little bit. You could see that in the really slow motion video, although, it's not very much. One is if the bullet comes out even a tiny bit off from horizontal, that'll make a big difference in how long it takes to hit the ground. We'll do a calculation like that in a second. And the second one is just they're using electronic signals to drop the bullet and shoot. And so if those are off a little bit for some reason, or the mechanism sticks or whatever for just a tiny, those kind of things affect it. But okay, so what? I have this going right. Okay, what about this? What if you did this experiment with, it works with bullets, what if you did it with a frisbee? So this guy drops a frisbee, this guy throws a frisbee. So think about that one. It doesn't work there. And that's because frisbees are designed to get lift from the air, It wouldn't work with a helicopter either, like if this helicopter was flying and this helicopter was dropped. But bullets don't have anything in them that causes lift, and that's why this works. This calculation, and we'll do some examples for at least the rest of today. We'll do some tomorrow too, I guess. Question? Okay, so let's say these bullets dropped, one's fired horizontally at 1,000 meters per second from a height of 1 meter. How long does it take for the two to hit the ground? How long does it take each one to hit the ground? Okay, so first let's do the dropped bullet. So there's the ground. There's the bullet. It's dropped from here straight down. This distance is 1 meter. Draw that bullet a little better. That's a big bullet. Well, this is just a one-dimensional problem. We've done a lot of problems where things are just dropped. So let's choose a 0 position. I'll choose it on the ground. A positive direction, I'll choose up. The time equals 0 instant when the bullet is dropped. Yep. So equals 0 is going to be when it's dropped. Our time t is going to be when it hits the ground. And based on that, there's 6 variables that we have to consider. So let's just go through these. T, A, P0, P, V0, and V. And let's think about what we know. Do we know the time it takes to hit the ground? No, that's what we're trying to find. Do we know the acceleration? Yep, it's free fall. Do we know the initial position? Yep, if you start at 0 and go 1 meter in the positive direction, you're at +1, so we know that. Do we know the final position? 0, yep. Do we know the initial velocity? That's right. And do we know the final velocity? No, it's not 0 because remember, maybe my wording might have. When I say time t is when it hits the ground, all of this only holds for free fall. So as soon as it actually hits the ground, we can't use the equations anymore. So really, when I say it hits the ground, I'm talking about the instant before it hits the ground, when it'll have some negative velocity that we don't know. You know, it'll be going, 4 miles per hour, whatever. So we don't know that. And now we're looking for an equation that has t in it, and everything else in it is known. So it looks like this one will work. P is equal to P0 plus V0t plus 1/2 AT squared. So P is equal to 0. P0 is 1. V0 is 0. 1/2 times acceleration is negative 9.81 t squared. And so we have that t squared is equal to 2 over, so 1 over 4.905, I think. And so t is equal to, take that square root, you get a plus or minus, and 0.455 seconds. And we're only dealing with positive times, so it's that. Okay, so now let's think about the fired bullet. So this time, what's the path going to look like? So here's the muzzle of the gun. And this obviously isn't drawn to scale because it's going to hit the ground a long way away. But it's going to follow a parabolic path. And it's going to hit the ground over here. We know that this distance is 1 meter. We know that the initial velocity vector is horizontal. To do this problem, we have to choose a location for our origin and an orientation for the coordinate system. The one I usually choose is on the ground, right underneath where the object is at time 0. You don't have to do that, but Okay, so based on that, oh, and we also have to choose our time equals 0. Let's make that the instant that it's fired. And our time, let's make that the instant right before it hits the ground. And let's list out these variables and see what we know. So first, time t, do we know that? No. Do we know the acceleration vector? We always know that in free fall. It's 9.81 meters per second squared down. Down in this case is the negative y direction. So this is 0, negative 9.81. Do we know the initial position? It's 1 meter in the positive y direction from the origin. So that's going to be 0x, 1y. Please stop me if you have any questions about where any of these are coming from.
I have a question.
Mhm.
I have a question, like why the initial position is like 1 in the y component.
Well, one way to think of position is the position vector is the coordinates of the object. So what are the coordinates? So at time equals 0, the bullet's just leaving the muzzle.
Yeah.
What are the coordinates of the end of the muzzle? You know,
So
ask yourself that. So it's just straight up the y-axis, a distance of 1 meter. Okay, do we know anything about the position at time t? That's right. We know that the y component of the position is 0. We don't know the x component. But I'm going to write this as p y is 0. Do we know anything about the initial velocity? Yes. We actually know all of it, and I'll show you how this works. So to get that initial velocity vector, here's our coordinate system. Oh, that was weird. There's the x-axis, there's the y-axis. And our initial velocity vector is horizontal with a magnitude of 1,000. Okay? So it's a vector like this with a magnitude of 1,000. And now we're just trying to come up with the components of that vector. So quickest way to think about it, and it's easy to do it this way if you have any vector that's along a positive or negative axis, is just think, okay, well, it's in the positive x direction, magnitude is 1,000, so it's positive 1,000, 0. Okay. But you can also use the sine and cosine thing. What's the angle that you have to go counterclockwise to get from the positive x-axis to that vector?
So like from the starting all the way, so be like 360.
You could do 360. You might as well just do 0, you know, because they're lined up next to each other, but 360 gives you the same answer. So theta is equal to 0. So this vector is 1,000 times cosine of 0, 1,000 times sine of 0, which gives you, you know, what I just said the answer was, because we know it's moving just in the positive x direction. This vector is 1,000 for x, 0 for y. And then what about the final velocity? Well, something you're going to notice as you do all of these problems, I'm just going to tell you now, you would notice it eventually, is since there's only acceleration in the y direction, there's no acceleration in the x direction, that's equivalent to saying the x component of velocity is constant. So really what we would see if we calculated the final velocity is that the x component would stay at 1,000. Okay? That's not realistic with a real bullet because there's a lot of air resistance, but that's what these calculations would say. But we're just going to pretend like we don't know anything about the final velocity. Okay, it's just going to make it easier for us to see what equations are going to work and what aren't going to work. So just keep, as you're doing the calculations, just always tell yourself you're surprised to see that the x component doesn't change. You know, the horizontal component doesn't change. You can be pleasantly surprised each time. All right, so here's what we have. So now that's the bookkeeping problem, kind of. This is what we know. We're trying to solve for t. And we have 6 equations, but 6 candidate equations. We're looking for an equation that has t in it, and everything else in it is known. Which of those 6 equations is going to work here? Anybody have a feel for that? Well, it's got to be, you'd think it's probably one of the position equations, because that's what we used for the drop bullet, and it is. And we're only dealing with the y components, so it's going to be the y component of that position equation. So we're going to use Py is equal to P0y plus V0y times time plus 1/2 AY t squared. And now plug in the values. So 0 is equal to 1 plus V0y is 0 plus 1/2 times negative 9.81 times t squared. And if you compare that to the equation we used in the first case, right now we have the same equation. Okay. And so the answer comes out the same. T is equal to plus or minus 0.455 seconds. The times we want the positive. And the thing is, since we used the y equation, the x component of initial velocity never even came up. Any questions about that? Okay, so next time we'll say that the horizontal gun, I mean, it's pretty hard to make that bullet fire exactly horizontally. Let's say we're off by 1/2 degree, okay? And we'll say that it's fired 1/2 degree up from horizontal, okay? And we'll do this same thing again. You think it's going to make a little, it's a small angle. Is it going to make a little difference or a big difference? Yeah, it is going to make a surprisingly big difference. So see if you can mathematically think of why that's going to be. What's going to happen there? Yeah.